6 basically and 7, you have a whole lot of formulas, but these formulas about conditional expectation, you shouldn't get too stressed out by this, because basically in terms of concepts, these are concepts that you studied in chapters 1 through 3. Yes? So if you just kind of remember that, it should all make sense why your formulas look like this. All right.
Are there going to be proofs at all, or no?
No proofs. Okay.
Prove the fundamental theorem of probability.
Okay, properties. So this is chapter 7. So properties of expectation and variance. There are a whole lot of them. And some of the important ones are, if you have this, then it's just A times the expectation of X plus B. If I have expectation of X1 plus X2 plus Xn is just expected value of X1 plus expected value of X2. So basically the expectations just add. With variance, first of all, what is variance? The formula, it is expected value of X minus the mean square. And an easier formula for that is expected value of X squared minus the mean square. Some of the important properties of variance are variance of AX plus B is just A squared radius of X. And I'll talk about variance of sums once we define covariance. Let's go with covariance first. Covariance and correlation. Covariance is just defined as the expected value of X minus the mean of X times Y minus the mean of Y. So it's the deviation of X from its mean times the deviation of Y from its mean. And an easier formula for calculations is this. So when you want to do calculations, I think it's easier if you just memorize this formula. And correlation is just taking the correlation coefficient, rho, is covariance of X divided by sigma X, sigma Y, where sigma X is just the square root of the variance of X, and sigma Y is the square root of the variance of Y.
What is the rho before the equal sign?
Rho. So this is a symbol for correlation coefficient. Rho.
Oh, okay.
Some of the properties of covariance of X.
Was that correlation?
Coefficient.
Okay.
Correlation coefficient. And that's denoted by rho. Covariance of X with X, basically if you use X here, you see that it's just variance of X. If X and Y are independent, then I already mentioned this earlier, the covariance of X and Y is just 0 if X and Y are independent. If you get your covariance of X and Y to be 0, you cannot conclude that X and Y are independent. So the conclusion only works in one direction. If they're independent, then their covariance is necessarily 0. Covariance I equals 1 to n xi and yj. That is just going to be the sum. 1 to n. You just take all your xi's with your different yj's and you calculate the covariance of these.
Dumb question. Second line over there, that's if they're independent, right?
Wait, where?
Second line, all the way to the left, all the way to the left.
Here?
Yeah. Up one line.
No, for means, for expectations, it doesn't matter whether they're independent or not. I'm just taking the expectation of x1 plus x2 plus xn. Independence is only when things are multiplied that you would need independence to get the expectation of a product to be the product of the expectations. But this is sum. And for sum, I mean, just use the formula. It's just a summation of x1 plus x2 plus xn times the probability mass function. Even if it's the joint thing. Okay, I'm not going to do all this again. Just remember that formula. Expected value x plus y. Okay, I'll do 2. Distribute that, you get so now this is only x. If I sum y, I can pull this x out. And you end up here with and that is just expectation of x plus expectation of y. So with sums, there's no real problem. You don't need independence, because what happens is when you look at this term, you sum out your y's. So you take the sum over all y's. This x isn't affected by summation over y. So you get summation over y of this, and that is just the probability mass function of x. Similarly with y here, if you sum out your x's, then if you sum out your x in the joint probability mass function, you just get the probability mass function of y. So then this just becomes the expected value of x plus the expected value of y. So you don't need independence for that. So remember, independence is only important once you start multiplying things. Then independence happens. But for summation, so nothing big in the end, but basically the same idea, you can generalize it to n.
I really wish I could write as fast as you can write.
Well, aren't you recording that?
Yeah, that's why.
So this is stuff we need to know for like a formula sheet.
So the formula sheet, so I'm giving you this comprehensive review. You can pick out whatever you want from this and put it on your formula sheet. But a formula sheet cannot exceed
8.5 by 11.
yeah, 8.5 by 11.
Front, back, and side.
Side, okay.
I have really thick paper at home, so you didn't say we couldn't use that. It's like an inch thick.
But remember, it's a sheet of paper. It can be thick, but it can be a box. So pick out whatever formulas you think are important, looking at the practice problems I've assigned, and so maybe you have to memorize some stuff and put down some stuff, or write really small. I don't know, up to you, but you pick out what you want from everything that I'm going over. I mean, I would think the important things to put in would be formulas for, say, the conditional density function or the conditional probability mass function, in case you have problems remembering that. So. that might be a good formula to put down, or a formula about the covariance. Okay, I was going to get to variance of this. So this might be worth putting down because to get exactly what the formula is involves some work. You've got to think about several steps. So if I ask you to find the variance of the sum, you can basically put your properties here together, that you can write your variance as the covariance of x and then use this formula basically. And what you would end up with is this. So this, I think, is a tricky enough formula that I consider putting it on the sheet. Plus twice covariance of xi and xj. If you don't want to put twice and you've got to sum over all I, if you want, you can replace this formula with sum over all I not equal to j, covariance xi xj.
Is that the sum where I equals j? The first one?
Yeah, that's just covariance of sum where I equals j.
Okay.
And when I equals j, basically then you get that covariance of, you basically get covariance xi, and that's just variance of x. So yeah, so basically this part is just sum over all I equals j, and you get that. So if you want to think of it, the way this formula is derived is I write it as I equals j, covariance of xi xj, plus that one is not equal. So this part just becomes this, and this part is that. Moment generating functions. Next is moment generating functions, and the definition of a moment generating function, the moment generating function of a variable x is a function of t that is just the expectation of t raised to t. That's the definition of moment generating function. Now, what you might want to put on a formula sheet, but first of all, is definition. And also the different formulas we've got when for the different random variables we work with. So it's basically binomial, Poisson, exponential, and normal. So for each of these, it might be a good idea to memorize your, or put it on your formula sheet, because you don't want to keep deriving this every time. This would is not obvious what the formula should be. So these are the things you might want to put on your formula sheet. P e to the t, 1 minus a. If x is lambda, and x of t is e to the lambda t minus 1. X is exponential lambda mx t lambda over lambda minus t, and this is only defined for t less than lambda. And then if x is normally distributed with mean mu and variance sigma squared, then your moment generating function is going to be e to the mu t plus 1/2 variance times t squared. Right, so why is it important to know the formulas for your moment generating functions? This is so that if I give you a moment generating function and it looks like one of these types, if you can write it in the form of these moment generating functions, you can identify the distribution. So that's why it's important to know the different formulas for your moment generating function. So on your formula sheet, I definitely recommend putting down the definition and the formulas for these 4 different cases, 4 different distributions. So far, the important formulas I can think of are, given the joint density, how do you calculate probabilities? Okay. It's just the integral over the region of the joint density. Given the joint density, how do you find the marginals? The formula involved in that. Then how to find conditional densities from the joint density. The condition for when something is when 2 random variables are independent. And then the definition of covariance, of course, a simplified formula for covariance, variance, and then the main property of covariance, and then you have the generating function definition and those formulas for your four different distributions. So knowing the moment generating function helps because of this property of moment generating functions. Oh, and one more thing with moment generating function. Once you calculate the moment generating function, you can use that to find the mean and variance. The mean is just the derivative evaluated at t equals 0. And if you take the second derivative and evaluate it at 0, t equals 0, you get the second moment. And you can use that second moment to calculate the variance, because if you remember, variance is just this minus the mean. So if you're given some distribution, you have to find the moment generating function. You can then use that to calculate the mean and then the variance. Well, you know what this is. This is just d dx d t of n x of t evaluated at t equals 0. And this is the second derivative with respect to t evaluated at t equals 0. And then you have these important properties of moment generating function. Moment generating function uniquely determines the distribution. I think there's a problem in there. Yeah, so it's problem 7 on your, so problem number 7 on the practice problem basically uses that. So I give you the moment generating function of a random variable is of a certain form, and then when you look at that, it becomes obvious that x has to be Poisson distributed. So basically, knowing this tells you that x must be Poisson with parameter 0.5. And this, I've asked you to find the probability that x is greater than or equal to 2. So this is going to be 1 minus the probability that x equals 0. Lambda, so other important property is if x and y are independent, then moment generating function of x plus y is just the product of the moment generating functions. Should be useful in calculating moment generating functions of sums. And then come to chapter 8. First thing is the Markov inequality. It says that if x is a non-negative random variable, then you can bound the probability that x is greater than or equal to a by this, provided a is greater than 0. If you know the mean and variance, you have other bounds, and that's given by the Chebyshev inequality. Chebyshev inequality says that if x is a random variable with mean, mu, and variance sigma square, we can bound the probability that x minus mu, the absolute value of that, is greater than or equal to a, is bounded above by sigma square over a square. Right. Another way you could use this is, so you have an upper bound on this. If your problem was about what's the probability that the distance of x from its mean is less than or equal to a, you can get a lower bound for this. Because I can write this as 1 minus this. This is bounded above, so this is bounded below. Again, another way you could write this if I bring it like this. The distance of x from the mean is k standard deviations or more away. And this is bounded below by 1. So it's just using the same thing. I can use it to solve problems like this on this. So this basically is bounded above by variance divided by k squared sigma squared. Sigma squared cancels. You just have 1 over k squared. So there are 3 ways to write the same thing.